Hello, my name is Brian Pontius. I am in MA 06 Lab Section Thursday, 11 a.m. to 1:50 p.m. And this is Lab Practical Exam number 1 for Lab number 3. Okay, as you can see here, we have a circuit with the motor connected to the computer. This lab vehicle. And we'll start it. We are not going to save anything because we have necessaries here. And as you can see by continuous oscillations, it's fairly stable. Now, three gains here. Proportional, integral, and derivative. And as you can see by these arrows, it's possible to change them. Now, let's do so. But first, a prediction. If I increase the proportional gain, there's not going to be any effect on this way. So let's see if I'm right. And it looks very much like I was right. There is no visual effect on the sine wave of the measured angle, which is rep. White is the desired angle, and it's not going to be affected by alterations in the gains. Okay, now we are going to decrease the proportional gain. I have a different prediction for this one. The amplitude's gonna decrease, and when it gets below 0, as in when it gets negative, it's gonna flip and then start increasing. Let's find out. And no noticeable change in the amplitude. Go to more. It looks like the amplitude has shrunk. Let's make it a bit more gradual. And now it's fairly obvious that the amplitude has decreased a lot. And unsurprisingly, proportional gain 0 means flat line. Now, let's go to negative and see if I'm right about it flipping and the amplitude starting to increase. Not quite. It's flat, meaning that this is designed for a negative proportional gain. And seeing it positive again helps to fix it. We'll restore it to 0.3. And next is the derivative. This one's a bit different.
Steven.
Now, a prediction. When I increase the derivative gain, the graph's going to move up. Let's find out. And, looks like there's an error here. I think I know how to fix things. Switch to square wave, and the response changed to it. Now switch back to sine wave. Now let's see what happens with the derivative gain. And it is, in fact, moving upward. It's moving upward fairly slowly, but it's moving upward. Now let's set it back to 0. Now, another prediction for the derivative gain. When I decrease it to a negative number, it is going to move upward yet again. Only this time, the wave itself will be upside down. Let's find out. And something off about this. Again. Let's switch back. Sometimes this happens, I don't get why. But now let's test it again. And well, you look at that. It moved upward. And as you can see by the fact that it looks like even though normally the peaks are fairly in line with the desired angle, now it's like they're opposite. It has, in fact, flipped upside in. Now, let's set it back to 0. Next, the integral gain. Now, a prediction. When I increase it is going to go flat. It'll just be a straight line. Let's find out. And will you look at that? It's a straight line. Set it 0. Let's set it back to 0. Okay, now let's try going in reverse. A prediction. It's going to flatline. It's going to go up to the top and stay a straight line when I make it negative. And will you look at that? Exactly right. Now let's set it back to 0. However, that can't be the end of the story. For indeed, what would be the purpose of the integral gain if all I could do was create straight lines? Now, you might remember earlier, I discussed proportional gain and how increasing it past 0.3 didn't seem to do anything. Well, maybe it can do something. Let's set it to an arbitrarily large number like 50 or so. As you can see, there's no real change in the sine wave. But let's see what happens when we do the integral gain this time. And it didn't go flat this time. And it took to 0.65 before it went completely flat. Although obviously increasing the integral gain did cause a shrinking of the sine wave. So let's set it back to 0. Now, going negative, I'm going to expect a bit of a delay before it flatlines. Let's find out. And as you can see, it's getting a bit higher. It's getting kind of high now. And okay, more. And now it's really close to the top. Now, let's set it to negative 0.6. Now it's pretty much touching the 5 line. Now let's set it to negative 0.65. And as you can see, the sine wave is being limited by the 5 line. Now, decrease the integral gain some more. And now you can see it's suffering. So, and again. And again. And it's flatline. It took until negative 0.9 for it to do it this time. So as you can see, while the proportional gain doesn't have a direct effect on the wave, it does have an effect on how quickly the integral gain alters the sine wave. And now we are going to switch to a square. At least for the desired angle. There's not much of a difference with the measured angle. Although it has moved to position somewhat. Let's reset the proportional gain to 0.3 as well. As you can see, no visual difference. Now, let's see what happens when we decrease it. I'm going to predict another flat line here. And it doesn't seem to be much of a difference. Of course, the amplitude is decreasing, but will you look at that. it's gone flat, but we sent it to 0. As you can notice, there's not much of a change here from earlier. Once again, the amplitude has decreased, and now it's a flat line. But let's see when it goes negative. Yep. Instantly flat lines. So we'll reset it to 0.3. Okay. Now for the derivative gain. I'm going to predict that instead of moving upward, it's going to just change amplitude. When I'm going to predict that increasing the derivative gain will mean a decrease in the amplitude. Let's find out. And look, the amplitude's decreasing already. It's getting smaller and smaller. Still small. And as you can see, the amplitude's tiny. Now, we'll set it back to 0. Now, I'm going to predict an amplitude increase and a phase shift. Well, no, an amplitude increase and a frequency decrease when I decrease the derivative, when I make the derivative be negative. And will you look at that? That is a large amplitude. But it's not moving, but there aren't a lot of peaks here. And that's the effect of the derivative gain when it's under a square wave. Now, back to the integral gain. I am going to guess that there will not be any changes to the integral gain. Let's find out. And instantly, it's just sticks at 0. Now, go back to 0. And, once again, I'm expecting a flat line when we make it negative. And it just flat. So send it back to 0. Now, I'm going to predict similar results when we make it a proportional gain. This time around, I'm going to do a proportional gain of 100. Now, let's just go with 50. That way we can eliminate any changes due to the different proportional gains. Now, increasing the integral gain, as you can clearly see. Amplitude increasing. And will you look at that? It just went into a flat line. A single straight line and an integral gain of 0.3. Now, going negative, I'm going to expect it to flat line, but with a delay. And, yep, it's going higher. And still higher. And still higher. And still higher. And well, look at that. It took it to negative 0.6, but it's flatlined once more. So we'll set it back to 0. And we'll set the proportional gain back to 0.3. And we'll set this back to a sine wave. And that's it.